Hello everyone. Welcome to welcome to the live stream of uh, my self-study series. So in this session, I'm going to design Twitter timeline and search. I wouldn't say I'm going to design, I would say I'm going to learn to design since I have been preparing while I'm streaming here on the spot. So the intent is clear. The intent is to keep learning and also help somebody who is in the process of learning. And most of the content with this channel will be mostly unfiltered and straight out of uh, what I'm thinking. This would give a realistic expectation for most of the engineers as opposed to the polished content that we can create. It's easier to go back offline and record the same things in a much polished way in a thought out process, but that wouldn't give the clear idea of the level of each engineer. Doing this way, this would expose, this would at least set the realistic expectation of how an engineer looks like and how the preparation looks like and how the progression as well. I'm I'm seeing that I'm able to make improvements with the day or couple of days of preparation alone. So yeah, anybody can see that progress and get encouraged rather than trying to be perfect from day one. Let's start. Let's start with this new concept or new system design, which is designing Twitter timeline and search. This should be somewhat similar to the one that we looked into in previous one, which is design pastebin. Both of the design will have a lot of overlapping concepts for sure. Other than that, let's dive in and see. We will follow the same. We are following the same material from that GitHub repository. Let's see if time remains, we can try to search from some other materials as well and learn something. Try to learn from elsewhere as also. But let's try to cover this one at the least. That's the least expectation from this session. And feel free to post any questions that you have. I'll be happy to answer. And if you want suggestions about some other materials, how to prepare, feel free to post it. Okay, so as we saw in the previous one, step one is to, okay, they have given this one, designing the Facebook feed and Facebook search are similar questions. That has the declaration here, add that. And then step one is outlining the use cases and constraints. The use cases and constraints. So first thing is functional requirements. We'll scope the problem to handle only the following use cases. So I would categorize it as functional requirements. And fun user should be able to post a tweet and service should push the tweet to the followers timeline. And next one should be User views the user timeline. User should be able to view his own timeline. View his own timeline. User should be able to access the home timeline as well. Activity from the one follows. Okay, and then user searches keywords and service has high availability. Users searches based on keywords. Okay, and non-functional requirements. So in the non-functional requirements, service has high availability. So this is a type of system where we will prioritize availability clearly above consistency. And traffic is not evenly distributed, but can be not evenly distributed. This is not the requirement, but this is like the constraints or assumptions. Okay, and here services have a high availability pushes tweets. Okay, these are out of scope analytics, and service strips out tweets based on the user's visibility settings and these things. At least this doesn't seem like obvious use cases that everybody wants to address. Unless it's mentioned, I don't think anybody would have bothered to mention it. So let's not highlight it in out of scope just for the sake of mentioning it. If these were like core functionality and if we were not addressing those, then we could have mentioned it here, but I don't see a necessity to mention it here. We can mention analytics, something which is kind of obvious in all the applications. We don't have to cover that in the current design. And then assumptions, traffic is not evenly distributed. Okay, posting a tweet should be fast. Fanning out tweet to all of the followers should be fast unless you have millions of followers. And then these are the other assumptions. Posting a tweet and fanning out should be fast. And next thing should be 100 million daily active users or 100 million active users and 500 million tweets per day. Which means 15 billion per month. Each tweet averages a fan out of 10 deliveries. Averages a fan out of 10 deliveries. And 5 billion total tweets delivered on fan out per day. How this number? So because each tweet averages a fan out of 10 deliveries, so 500 million tweets per day, 500 multiplied by 10, that would be 5,000 million tweets, 5,000 million fan outs, that means 5 billion fan outs per day, and then 150 billion tweets delivered on fan out per month. Okay, so 15 multiplied by 10, the 150 billion fan outs delivered per month, and 250 billion read requests per month. 250 billion read requests per month, and then 10 billion searches per month. Okay, 250 billion reads per month and 10 billion searches per month. Okay, it is pretty read heavy if we compare it to 15 billion reads per month and then 15 billion per month, 15 billion tweets per month. Okay, and timeline, viewing the timeline should be fast. Twitter is more read heavy than write heavy, optimized for fast reads of tweets, and ingesting tweets is write heavy. So here, more read heavy than write heavy, optimized for more reading, or optimized for fast reads. Okay, so these are kind of good enough assumptions and functional and non-functional non-functional requirements. And so about searching, searching should be fast, and searching is read heavy. So searching is read heavy as well, and read heavy and fast. Calculate the usage. So let's see, like the last problem itself, let's come up with the basic model. We can tweak it later at a later point of time as we dive into more details. But for now, let's assume the basic information and try to estimate that. Clarify with the interviewer if you should run back of the envelope usage calculation. If yes, let's make the assumption here. Back of the okay. So here we are seeing this one. Okay, let's calculate the size of the tweet. How to go about it? Let's see this way. So size of the tweet. What does the tweet consist of? So one, it will have a tweet ID, any identifier as such, and then who tweeted it, that is the user ID, and then the text, and then the media, that's option, which is optional. Okay, user ID, and then media posted at, and the most important thing, the tweet or text itself. Okay, So let's say the tweet ID is 8 bytes and user ID is 32 bytes. 32 bytes. Then the tweet itself could be 140 letters. That was the restriction before. So 140 bytes. And then the media can be 10 KB on an average. And posted it can be somewhat like 5 bytes or something like that. So total in front of this 10 KB, everything else is kind of negligible. So on an average, it will be like 10 KB per tweet. But yeah, media is not that significant. I think we can just remove this and try to handle only the text tweet, and media we can handle separately, because we do not even have to store that in the same database table. So we could have estimated or calculated it separately. So we don't have to follow it in the same way as well. So here it's mentioned 150 terabytes of new tweet content per month. Okay, this is the total value, but which one we are more concerned about which one goes to the database directly and which one goes to some object store separately. So here they are mentioning 150 TB of the new tweet content per month, 10 KB per tweet, approximately like multiplied by 500 million tweets per day, multiplied by 30 days. That makes a data of 5.4 petabytes of new tweet content in 3 years. So where this number came from, 150 terabytes of new tweet content per month. So 150 multiplied by, make it 150 multiplied by 36, 36 and multiplied by 150. So that makes it 5,400 terabytes. That means 5.4 petabytes of new tweets in 3 days. Okay, and 100,000 read requests per second, 250 billion read requests per month. This makes it 250 billion read requests per month, because 2.5 million seconds per month. There are 2.5 million seconds per month. Okay, that's mentioned here. So 2.5 multiplied by 100,000. So that would make it as 2.5, 250 billion read requests per month. And then here I don't know what this one is, 400 read requests per second by 1 billion requests per month. Okay, we can get to this one. And then 6,000 tweets per second. 6,000 tweets per second. How did they come across this one? 15 billion tweets per month multiplied by 400 requests per second divided by 1 billion requests per month. $400 requests per second. Where are these two numbers coming from? That's my question. 400 requests per second. That is 1 billion requests per month. Okay, that makes it 100 read requests per second. Okay, they have given the total number of read requests per month, or we have the total number of read requests per month here, and we are calculating the total number of read requests per second based on that. Got it. So this would make it 100,000 read requests per second and 6,000 tweets per second and 60,000 tweets delivered on a fan out per second. And here 4,000 search requested per second, 10 billion search per month, and then okay, divided by the time to convert it to per second than per month. This makes sense, but do we need to capture all that? Okay, let's try to follow that exercise and try to learn from it. Total is approximately 10 KB here. And let's come to this one. This one is heading 2 for us. Okay, and here next bullet point is this 150 terabytes of new tweet content per month. Okay, how is that reduced? 10 kilobytes per tweet. Okay, there's some problem with the screen width now, or the window width. Okay, I hope it's better now. Let's keep going. Let's keep going here. To come up with the back of the envelope calculation, I think it's the key is to practice. We need to keep practicing that. Size of the tweet. How did they come up with the size of the tweet? Okay, we have the tweet ID. Okay, we have this as the size of the tweet. Now we need to address there is an assumption that there can be 10 KB. The size per tweet is 10 KB. Then there are 5 million or 500 million tweets per day. Tweets per day. And there are 30 days in a month. So that makes it 150 terabytes of new tweets per month. Terabytes of tweets per month. Okay. So we need to calculate the storage efficiency for 3 years. Usually that's the standard practice. The total storage that we need for 3 years. How do we calculate that? 150 multiplied by 36 months would make it 5.4 petabytes for tweets. Petabytes of tweet content for 3 years. Okay, this is clear. So now the next thing that we can calculate is the number of read requests per second. So we know that there are 250 billion read requests per month. That is given in the constraints or assumptions that was taken. 250 billion reads per month. And then how can we convert per month to second? So there are 400 requests, 250 billion read requests per month. Okay, 250 billion reads per month. And then per month, how many seconds are there? 2.5 million. So what would that make? Okay, so okay, per month divided by 2.5 million seconds. That should give, okay, 250 billion, 2.5 million. So 250 billion is nothing but 250,000 million. 250,000 million and 2.5 million. So that would end up with 250,000 divided by 2.5. Okay, so that would make it 100,000. Yeah, 100,000 read requests per second. It's a good calculation. Nice, improving. And then it says 15 billion tweets per month. How did we get that value? Here we have 500 million tweets per day. So that makes it 15 billion tweets per month. So if there is 15 billion tweets per month, that makes it 15 billion divided by 250 or 2.5 million. That would make it 15 billion means 15,000 million. 15,000 million divided by 2.5 million. So 2.5, 6 times. 6 times is 15. And yeah, and it makes it 6,000. So what is this? 15 billion tweets per month. That makes it 600 tweets per month. And if that's, 6,000 tweets per second. That makes it a requirement of 60,000, 6,000 tweets per second multiplied by 10 average fan outs per tweet, which makes it 60,000 tweets delivered on fan out per second. Okay, that's perfect. And then there are 10 billion searches per month. 10 billion, that means 10,000, 10 billion, let's keep it that way, searches per month, which makes it 10,000 million searches per month, 10,000 million divided by 2.5 million, 10,000 million divided by 2.5 million seconds per month, which gives 2.54 times, and 2.54 times is 10, so 4,000 times this one, 4,000 times 4,000, 40,000, 4,000 searches per second. Okay, our search requests per second. This is cool. Yeah, so all of this we could calculate just by knowing one simple thing. There are 2.5 million seconds per month. Okay, so that's the main thing, or the main assumption. Okay, this is cool. We have the back of the envelope, kind of back of the envelope calculations about how many requests that we need to handle per second. Let's create a high level design now using all this data. So in order to create the high level design, it's kind of same thing for every design that we go through. We will have a client, and we will have a web server, and we will have a separate APIs for read API and write API, and then we have a search API in addition here. There are multiple downstream services which handles all those read APIs and write APIs, like there is a timeline service, there is a tweet info service, and there is a user info service. And for write API, there is a fan out service which has a user, which tries to connect to user graph service, and then the search service, and also the notification service. And then the search API that just connects to the search service. And then the fan out service has connection with the in-memory cache as well as the object storage. And this read API is reading from the MySQL, and then this write API is directly writing to this MySQL as well. And the fan out service is mainly connected to memory cache. That information would come handy when we try to scale out our approach. So let's represent this one. Should I try to create it again? Okay, let's look into this once again. There is a web server, there's a client connecting to web server, and there are read APIs and write APIs. That timeline service supports the read APIs, and it is connecting to connecting to an in-memory cache, as well as the other services like tweet info service and user info service, in order to create that timeline. And the read API reads directly from the database table as well, other than these. And the write API, coming to the write API connects to the MySQL database directly, as well as it is invoking the fan out service as well. Fan out service in turn either stores it in the object store or in the in-memory cache as well. Also, it has connection with user graph service, search service, and notification service in order to render that or in order to deliver that data or deliver the new tweet information. And then there is a search service this side, which is connected to only search service. There is search API which is connected to only search service. So let's have this one represented. Create a high level design. in the next step here. Okay. Yeah. So it is kind of self-explanatory, whatever I mentioned. There's nothing else mentioned in here in this repository. Okay, design core concepts. So under design core concepts, usually we either design the data models, API design, and other data flow related concepts. Let's take a couple of minutes break and then let's dive into this design core concepts. Let's take a short break of 5 minutes. Okay, uh, let's get back to the problem now. So, yeah, where were we? Yes. We just came up with the high level design. I mean, we just read about the high level design and now we wanted to design the core components, or we wanted to go through the design of the core components. Let's do that. Okay, here, while designing the core components, dive into details for each component. So each components that we saw here, whatever was there, let's talk about each of those based on the use cases. Use cases, user posts a tweet. When a user posts a tweet, we could store the user's own tweet to populate the, okay, user posts a tweet. We could store the user's own tweets to populate the user timeline. Okay. Activity from the user in a relational database. We should discuss the use cases and trade-offs between choosing SQL and NoSQL. Okay. Delivering tweets and building the home timeline. Delivering tweets and building the home timeline. Activity from the people the user is following is a bit trickier. Fanning out tweets to all followers, 60,000 tweets delivered on fan out per second, will overload a traditional relational database. We will probably want to choose a data store with fast writes such as NoSQL database or a memory cache. Reading 1 MB sequentially from memory takes about 250 microseconds, while reading from SSD takes 4x of that. And the disk takes 80x longer. We could store media such as photos or videos on an object store. The client posts a tweet to the web server running as a reverse proxy. The web server forwards the request to the write API server. The write API stores the tweet in the user's timeline on a SQL database. The write API contacts the fanout service, which does the following. Okay, queries the user graph service to find users followers stored in the memory cache. Queries the user service to find users followers stored in the memory cache. Stores the tweet in the home timeline of users followers in a memory cache of an operation. There are 1,000 followers means 1,000 lookups and inserts. Okay. And stores the tweets in search index service to enable fast searching. Okay. So stores the tweet itself in the search index service to enable faster searching. Stores media in the object storage. Okay. Uses the notification service to send out push notification to followers. Uses a queue to asynchronously send out notifications. Okay. So the notification service should handle it asynchronously. Okay. These things are clear. Let's see other points. Clarify with the interviewer how much of the code you are expected, right? If our memory cache is Redis, we could use a native Redis list with the following structure. Tweet n plus 2, tweet n plus 1, tweet n. Here tweet ID, user ID, and then the metadata. Tweet ID, user ID, and metadata, 1 byte. 8 bytes, 1 byte. Okay. The new tweet would be placed in the memory cache, which populates the user's home timeline. Activity from people the user is following. Okay. We will be using a public REST API, okay, in order to test it. So we are posting, that means we are creating a tweet, and that would send out a response as a tweet itself. For internal communications, we can use something as RPCs or gRPCs that we looked into in our previous session. Okay, let's reiterate this first component, first use case, which is user posts a tweet. So this is part of the step 3, where we design the core components. Design the core components. Okay. Here, let me explain the steps one by one. First use case. First use case, what is it? It is user posts a tweet. Okay, not user case, this should be a use case. And the next use case can be user views the user timeline. User views own timeline or own activity. And then the next following use case can be user views home page or all the other timelines. Basically, user views the home timeline or activities from the follower user that one follows. Okay, and another one is user searches with a keyword. That should be another use case. Okay, user searches keywords, user views the user timeline, and then user views the home timeline, and here user creates the tweet. Okay, they have handled this. This is a little more complicated use case. They have handled this one before this. Let's follow the same order. Okay, now the first thing is user posts a tweet. So what all things that need to be considered in that use case? Whenever a user posts a tweet, first thing is we need to populate the user timeline or the activity from the user, and that can be stored in a relational database that is represented in this case here. So whenever the client make a call to the web server, that comes to the write API write API via web server or the reverse proxy. This web server is nothing but a reverse proxy. This is routing the request to the write API, and then this write API is writing to the MySQL database directly. So and another thing is we should discuss the trade-off between choosing SQL and NoSQL. So how did we define or how did we see a tweet should be? A tweet will look like something like this. It will have a tweet ID, user ID, text, and a media, and then we will have user tables which maintains the user details, and also there will be followers table which will have the users and the list of users that one follows. Yeah, so all these have some kind of relationships, and it's kind of and also we need to be able to join multiple tables in order to run certain queries, like borrow all the most recent activity from all the users that this particular user follows. So those are kind of things, or the queries, complex queries that need some relational database, or that need some good SQL support. That's why we can go with the relational database or SQL database in this case. And also for scaling, we are using some other methodologies, like using an in-memory cache in order to do the fan out or push the updates to user timeline and all that. So scaling should not be a bottleneck as well. So we can go with that assumption, and we can use the MySQL here. Okay, once that decision is made, write API is writing to that MySQL database, and delivering the tweets and building the home timeline, that is another beast, or that is the main one of the use cases that we need to follow. So in order to do that, fanning out the tweets to all the followers, that is most important. So fanning out the tweets to all the followers, how is that handled? That is handled by that has a potential to overload the relational database. So that will be handled by having some fast NoSQL database in memory, something like Redis or a memcache should work for this use case. Reading 1 MB sequentially from memory takes about 250 seconds. Let's say, okay, we can store the user's own tweets to populate the user timeline. In order to do that, we can query from the SQL database. For this, we can store the tweets, store the user tweet in a SQL DB, and then delivering the tweets and building home timeline by fanning out the write to all the followers might overload the traditional, not just relational, even if it was NoSQL database, it had the potential to overwhelm some of those databases, traditional relational databases. So in order to avoid it, that's why we can we can use a fast in-memory NoSQL or an in-memory cache. Okay, so once this is done, we could store the media such as photos or videos in an object source. That's another thing that we have represented in the design here. When the write API writes to MySQL, the fanout service stores the media into the object store. We can store the media media such as photos or videos on an object store. Okay, now the sequence of event happens is the client posts the tweet to the web server or reverse proxy. That is in the first layer here. Client is posting the tweet by connecting it to the reverse proxy. And then the second step, the web server routes the request to write APIs. Okay, and then what write API does? Write API does, it stores the tweet in the user's timeline or the user activity table in the database. First thing is the write API stores the tweet in the user activity table, or it can be user tweet table also, the SQL database. And once that is done, the write API connects with multiple different API. The write API connects with multiple different services. Connects with fan out via fan out service, as represented in the blocks here. So write API writes to the fan out service, and fan out service invokes the user graph service, search service, and then the notification service, and also writes it to the in-memory cache and the object store as well. So here, first thing is fan out service queries the user graph service to find the user's followers, and then stores the tweet in the in-memory cache in the timeline of users followers. So the timeline is kind of readily prepared and kept in in-memory cache to improve the performance. So that those timelines are updated, or this new tweet is pushed to their home timeline. So how does in an in-memory cache, okay, store the tweet in the timeline of users followers, or tweet in the users followers timeline in an in-memory cache. Okay, that would be the next step. Once that is done, store the tweet in the search index as well. Text service to enable fast searching. And stores the media in the object store. Uses the notification service to push out the notifications to followers. So this is all things that the fan out service does. And then if our in-memory cache is Redis, we could use a native Redis list with the following structure: tweet 1, tweet n plus 2, tweet n plus 1, tweet n plus 2. Okay, so this is like a Redis list with the following structure. Okay, the new tweet would be replaced in the in-memory cache. The new tweet would be replaced in the in-memory cache, which populates the user's home timeline. Activity from the people, the user is the following. Okay, activity from people, the user is following. The new tweet would be placed in the memory cache, which populates the user's home timeline. Okay, activity from the people, the user is following. Okay, that makes sense. I think that's that we captured in here. Store the tweet in the user's followers timeline in an in-memory cache. Okay, And then we will use REST APIs. So, okay, we'll use REST APIs to test it, and then this will be the response, which consists of created at status, tweet ID, and user ID. For internal communications, we used RPCs. And then the next use case. Let's come to the next use case. User views the home timeline. When the user views the home timeline, what all things should happen. Okay, let's make these use cases as, first thing is let's make this step 3 as heading 2. Yeah, and then this one could be our heading 3. Okay, when we come to this one, user views the home timeline, activities from the user that follows. So here the client posts a home timeline request to the web server, and then the web server forwards the request to the API read API server. Okay, once that is done, that it will contact the API service. The read API server contacts the timeline service, which does the following: gets the timeline data stored in the in-memory cache containing the tweet IDs and then the user IDs. Okay, that is of one. And then queries the tweet information service with the multi-get to obtain additional info about the tweet IDs. Okay, only the tweet IDs are pushed out here, but the tweet information service would get the information about all those tweets or query the information about all those tweets often. Okay, multi-get. Let's see quickly what is multi-get or mget. Okay, returns the value of all the specified keys for every key that does not hold a string value or does not exist. The special value nil is returned. Because of this, the operation never fails. Okay. Time complexity is open, wherein is the number of keys to retrieve. Read string fast. Okay. Makes sense. Queries the tweet info service with a multi-get to obtain additional info about the tweet IDs, and then queries the user info service with a multi-get to obtain additional info about the user IDs. Okay. Once that is done, it will generate the timeline. Okay. Makes sense. Now this examples make sense to me. Here also, like post request with this data, with all this tweet data, and that will provide a response like this. Let's capture it. There's no harm in that. Post request with the data created at placeholder Wednesday, September 02, 1998, 5 p.m. Let's correct the format later. And then status okay. Now the next thing is status. Status could be anything. and here's the tweet ID. Okay, random kind of UUID, and then there should be a new user ID, and that would be random as well. So this would be a post request. And then here we are making a get request in order to get the user details. So this will be like get, this will be like post tweet. Post tweets, okay. And then this will be like, this will, the rest convention would follow. Get tweets, or get timeline for user with user ID. Okay. How is this represented? User ID. Yeah, it will be somewhat like something like this. And then the response will be user ID. Tweet ID. Why is this called tweet status instead of text? Let's mark it as, what did we call it here? We called it as text here, so let's call it as text instead of status. Confusing there. So text system design practice. Okay, we can create one more here. Okay, so this could be the text or the tweets and a sample response here. And then for this use case, what are the sequence of steps that happens? The client posts the home timeline or request for home timeline to the web server. Web server forwards the request to the read API server. Okay, so now the read API server contacts the timeline service that we saw here. Contact the timeline service, and then timeline service takes care of the rest of the things. Timeline service, first what it will do, gets the data stored in the memory, in the in-memory cache, containing the tweet IDs and user IDs. Okay, that is neat. And then queries the tweet information service or tweet service, it can be tweet info service, to obtain the additional information about the tweet ID, providing the tweet IDs. And the same thing it does for the user IDs as well. Queries the user info service to obtain the additional information about the users. Okay, and we have the request example here. So that is done, and then the user views the home timeline. For this one, this is one simpler use case relatively. So the client requests for a home timeline to the web server, and then the web server forwards the request to the read API server. Once that is done, the read API retrieves the user timeline from the SQL database. Okay. The REST API would be similar to the home timeline, except all the tweets would come from the user as opposed to the people the user is following. Yeah, makes sense. So it will look something like the same thing. Get own timeline, let's say get own timeline, and then give the user ID. So user ID, let's say whatever is given, the same user ID will be here, and then the tweets that were there, my self-test and practice, my coding practice. Okay, this will be returned as a response. Okay, once this is done, Okay, so this one is done. Next thing is searching. Let's see how they have handled the search here. The client sends a search request to the web server. The web server forwards the request to the search API server. The search API contacts the search service. We can see here. Client sends to the web server sends the request to the search API. Search API sends the request, contacts the search service, which does the following: parses or tokenizes the input query, determine what needs to be searched, removes markup, breaks up the text into terms, fixes typos, and normalizes capitalization, converts the query to use Boolean operations. Okay, queries the search cluster, that is Lucene, for results. Scatter gathers each server in the cluster to determine if there are any results for the query, and merges, ranks, and sorts, and returns the results. Makes sense. This is detailed. This is the way to present any search service. I would have had lots of words even if I know the concepts of information retrieval. Okay, this is nice. Let's capture it here. So the sequence of events is the client sends the request to the web server. That's the common thing. Everything is getting initiated from there. And then the web server forwards the request to the search API server. Okay, once that is done, the search API contacts the search service and search the service does the same thing, parses or tokenizes input in the input query. How does it process and tokenizes this one? So by removes markup, breaks up the text into terms, that is tokenization, and then fixes typos if present. Normalizes the capitalization. Converts query to use Boolean operations. Okay, I do not understand this much, so let's not bother about this for now. And then it queries the search cluster. Looking for the results. So what that does, searches each server in the cluster to determine if there are results matching the query, and then merges, ranks, and sorts. Break on the results. Okay. So one more thing pending is we should look into the details of leucine sometime when we get time. It would be a good exercise to look into Go Apache leucine and try to understand the basics of it. This looks a little boring, I guess. So we can see. Okay, I like this one. Okay, I like these materials. We can just go over those. I'll mark it for read later. Okay, got it. Let's go back to the Twitter timeline. Okay, for some reason it's not loading. Got it. So next thing is scaling the design. For scaling the design, we use the similar approach that we did in the last way, or the last problem. Here it was anyway elaborate, like we kind of delegated the task into different services like user graph service, search service, notification service, fan out service, and we had an in-memory cache already which was taking care of the performance, and then SQLs, but we didn't elaborate it as read replicas and then the write replicas, write optimized ones. And these ones we didn't show it as distributed ones or having multiple instances. Now we are showing it as having redundancy here. And then we have a CDN as well, which can be used to um, connect to the object store or cache the data from the object store as well. So yeah, so this is like these are the improvements, and we will be discussing similar concepts about load balancers, CDN. Like as we understood, CDNs are the okay. We can go one by one. CDNs are the ones which would provide much performant results by staying closer to the geographical location of the user and acts as a caching layer. There are a couple of strategies: push and pull. So when we have push strategies, basically everything that we write to the object store, we should deliberately write it to the CDN as well and modify the client URL to use the CDN. And then pull model pulls from the object store upon the first request from the user. So yeah, a few offerings are AWS CloudFront and Cloudflare, if I would like to say. Yeah, these are some of the popular choices for DNS. And load balancers. Load balancers basically has multiple types of load balancing strategies, but yeah, it is evenly distributing the load across the web server, and there will be multiple instances of web server, and the load balancers are just represented here, but there will be load balancers in each of the services, since each of the services has multiple instances or multiple workloads managing the traffic, and the load balancer in front of it would route the traffic uh, to the appropriate instance, and also manage the healthy fleet of instances and retire the other ones. Yeah, and then SQL read replicas, and these are the read optimized one, and then the master write replica. So whenever the write API writes to the master, it will take some time to replicate it into the read replicas, but the read APIs are reading directly from the read replicas only. Then we can see that the fan out service is writing to the object store directly, and also to the cache service. And whenever the client wants to retrieve some static assets, it can just contact the CDN or for the same results as well, and then it will connect to the object store. Let's gather this same data, and this is, what is this called, scale the design. So that's the next part. So this is step 2. Yeah, it's mostly representing all this in this one, but I did not see a lot of change or improvement over this one. They have just mentioned a load balancer layer and showed multiple instances in each of these services, and showed the read and write replicas for the database table, and also a CDN and DNS layers here. That's the only change I see. Okay, so let's go over the text that they have written here. Important, do not simply jump into the final design from the initial design state. You would, okay, these are the obvious things. It's important to discuss what bottlenecks you might encounter with initial design and how you might address each of them. For example, what issues are addressed by adding a load balancer with multiple web tokens, CDN, master slave replicas. What are the alternatives and trade-offs for each of those? We will introduce some components to complete the design and address scalability issues. Internal load balancers are not shown to reduce clutter. To avoid repeating discussions, refer to these things. The fan out service is a potential bottleneck. Twitter users Twitter users with millions of followers could take several minutes to have their tweets go through the fan out process. This could lead to the race conditions with at replies the tweet, which we could mitigate by reordering the tweets at the serve time. Okay. We could also avoid fanning out tweets from highly followed users. So avoid fanning out tweets from highly followed users. Instead, we could search to find tweets for the highly followed users, merge the result or merge the search results with the user's home timeline results, then reorder the tweets at serving them. This is a good idea. Rather than keeping redundant copies of the same thing from highly followed celebrities or highly followed users, we can just keep the user timeline separately, and then the search results of the highly followed users, and then we can merge that result and render the home timeline. Additional additional optimizations include keep only several hundred tweets for each home timeline in the memory cache. Keep only active users home timeline info in the memory cache. Okay, these two. Keep only several hundred tweets. So there will be definitely a question that, okay, if we have maintained an in-memory cache, what all data that we will prioritize to keep, because memory cache will have about, like, it won't provide that infinite amount of data storage for us. This will be limited, so we should use it more carefully, and we should treat this as a precious storage and use it accordingly. um, Yeah, there are several strategies that they have been discussing here. Keep only several hundred tweets for each home timeline in the memory cache. Keep only active users' home timeline in the memory cache. If a user was not previously active in past 30 days, we could rebuild the timeline from the SQL database. Query the user graph service to determine who the user is following. Get the tweets from the SQL database and add them to the memory cache. Okay. Store 1 month, only a month of tweets in the tweet info service. Okay. Store only active users in the user info service. The search cluster would likely need to keep the tweets in memory to keep latency low. We will also want to address the bottleneck with SQL database. Although the memory cache should reduce the load on the database, it is unlikely the SQL read replicas alone would be enough to handle the cache misses. We will probably need to employ additional SQL scaling practices. The high volume of writes would overwhelm a single SQL write master slave, also pointing to a need for additional scaling techniques, federation, sharding, and denormalization. So it's easily sharded based on the geographical location or some using some strategies here. Okay, so let's capture these points. There are some good points here. Yeah, these are generic ones. The fan out service could be a potential bottleneck here. Twitter users with millions of followers would take a long time to have their tweets pushed through the fan out process. Okay. So now in order to avoid it, we could avoid it by not fanning out the tweet from the users with the large following, but we could search to find the tweet and the tweets for highly followed users and merge the search results with the user's home timeline. Okay. Additional optimizations. Keep only several hundreds of tweets in the in-memory cache. Keep only the tweets only the home timeline of the active users. If a user is not active for over 30 days, we can render their timeline using the SQL queries. Okay. So only a month of tweets in the tweet info service, not tweet info service. So only the active users, the user info service. The search cluster would likely need to keep the tweet in memory to perform better. Okay, through the in-memory cache, and we will also want to address the bottleneck with the SQL database. Although the in-memory cache should reduce the load on the database, it is unlikely that SQL read replicas alone would be enough to handle the cache misses. Okay, even though we have in-memory caches to reduce the burden of the SQL databases, that might still not be sufficient to handle all the cache misses, and we should think about other scaling techniques in order to handle, in order to make the queries more performant. Okay, other scaling techniques, I would say sharding, federation, denormalization, etc. Okay, this looks good. So rest are same. So yeah, this is good. I'm enjoying it. But we can look into other alternatives as well. So for the next design, let's go over something like Hello Interview or educative.io, so that we can get perspective from the from different sources in order to create a design. So I think this should be comprehensive for this particular design. Let's see. Yeah, that should be it. Yeah, we can follow different approaches tomorrow when we're handling the other ones. It's already late. I'm going to end the stream for today. If you have any questions, feel free to post it in comments. And if you need any suggestions while preparing for the interviews, I think I have time to talk about it. You can contact me directly. And also, if you have any suggestions for me about how I can make these content much more interesting and much more useful for the one who is spending time watching it, then I'm all ears, and I'll try to adopt in my future live streams or future versions of the content. Thank you very much. Stay curious, keep learning, and let me make this one formatting change before I end the night. Good night.